sequences. So when we talk about sequences, we're looking at a pattern of numbers. So if I go 1, then 3, then 5, then 7, what am I doing every time? Then 9, then 11, adding 2s, right? So we're talking about a sequence. That's like a very simplistic example of a sequence, but it's a sequence. We're going to talk about summation notation, but actually not today. We're going to talk about summation notation in a lesson. It's still going to be in 12.1, but it's not today. So we're going to get partway through 12.1. We're not going to get through all of it. Yeah?
Didn't we just do module 9?
Yes.
That's a good note.
Doesn't 12 come after 9? So when we get a textbook for a class, we follow the textbook for the most part, but the state of Michigan also says, this is what you have to teach to call it pre-calc. And so we are going to come back to 10, but it's about matrices, and the state of Michigan does not ask high school to teach matrices at all. Like, it's nowhere in our curriculum. Okay, so the stuff that we skip over is for a reason. It's not like, let's fast forward, we don't have much time. Okay, so we purposely go through it. So again, when we buy textbooks, we look for textbooks that fit as closely as possible to what we need, but we don't need everything. All right. So listening, please. When we are looking at a sequence, we are looking at situations. We're looking at situations where our domain is the set of natural numbers. So remember, natural numbers are the same as counting numbers. So if I asked you to count, what number would you start with? 1. So natural numbers are 1, 2, 3, 4. It's just how you would normally count. You don't normally start with 0. 0 is not a natural number. So we're starting with 1 and going up. The reason being is because if we have a sequence, we're going to think of them as terms. So you have your first term, and then you have your second, and then you have your third, and then you have your fourth. Okay, so we think of them, we don't have like a term 3.5. There's nothing that like squeezes its way in the middle. So our domain is always going to be counting numbers. We're not going to deal with 0. We're not going to deal with negatives. Always counting numbers. So that's different from a lot of the other stuff we've been doing where those were still on the table. So what is the notation for a sequence? So the way that we word a sequence is A sub n. And n, that subscript n, so it looks like A and N are on the same line there. I should have done a better job at making it a subscript. That should be an A with a subscript of N. So A sub N is going to be our notation instead of F of N. A sub N. So it should be, let me make it more exaggerated. So I mean like this, A sub N, like this. So A sub N instead of having like a function of a variable. So again, we're doing counting numbers for our terms. So your terms are going to be A sub 1. You start with term 1, and then term 2, and then term 3, and then term 4. There are a couple different types of sequences that we have out there, just ways we set them up. One is more of an explicit formula, and then the other is what we call recursive. I'm going to show you both of those today. And there are benefits and drawbacks to both of them too. All right, next. There's just a lot of writing, so I figured I'd write it ahead so I could just kind of talk and explain it. So this is the last bit that's just like a lot of writing. Then we're going to do some problems together. So the main difference between like a function that we have out in the world and a sequence is the domain. So when you have a function like x squared, that one would have a domain of all real numbers, and we would connect the points. When you have a sequence, you only have natural numbers for your domain, and we do not connect the points because the stuff stuff in between isn't a part of it. So we have a term at a sub 1 and a term at a sub 2, but they aren't connected because there's no in between. There's no like a sub 1.5. So there's no connection. They're separate points. So they are natural numbers and we do not connect the points. But for these graphs, like if you had x squared, we would connect the points. So we're going to do an example. Again, they start pretty easy. I think the trickiest part probably in this whole chapter is a lot of the formulas get kind of similar again, kind of like what we saw in chapter 9. And so knowing when to use which formula and also like being able to differentiate between the two because they're so similar. So I'm going to show you what I call more of an explicit formula. Like I'm going to give you the formula and you can use it as is. There, like I said, is another type of formula called a recursive formula. I'll show you that second. So let's say we want to find the first 5 terms and also the 150th term. And this is our formula. Okay? So if I'm given that, let me get a pencil. When I go to find a sub 1, right, term 1, do you see how the 1 is where the n was? Okay, so I'm going to plug the 1 in where the n is here as well. 8 times 1 is 8 minus the 2, 6. So term 1 is 6. I'm not going to write all of them out, but I just want to show you where it came from, right? So I'm just plugging in the 1. So if I go to find the first 5 terms, then I also need to find a sub 2, a sub 3, a sub 4, a sub 5. Also, as a side note, I just feel like this is worthy of saying, I feel like this is covered more heavily than the other sections on the exam as well. Like I feel like there's more chapter 12, even though it's only 3 sections. So just make sure you're understanding, because like I said, I think it's going to come at you hard on the exam. Okay, so a sub 2, if I plug in 2, what am I going to get? 16 minus 2 is 14. Okay, so then we're going to plug in again. We should get 22, 30. What else? Yeah, you're adding 8 every time. Somebody notice that you're adding 8. Yes, because 8 is acting like your slope, basically. It's your rate of change. Okay, so what's A5? 38. So you're always going to notice a pattern like that. That's not a coincidence. Like, ooh, look, this is a cool, super easy one. They're going to have patterns for the most part, and you're going to be able to look at them and say, like, okay, this is what's happening, and you won't have to do quite as much calculation. All right, can I jump ahead and find the 150th term? What would I do? Yeah, you just plug in the 150, right? So 8 times 150 minus 2 should give me 1,198. So the nice thing about the explicit formulas is that you can plug in very easily any term, and you can jump ahead. Recursive formulas don't work as easily. So you can only find them based off the previous term, so that makes it a little tricky. Okay, again, let's make sure we're listening. All right, what if you have a -1? We're going to think about how that would impact it if it was being raised to a power. So let's just think about -1 for a second. If you had -1 to the second power, what is it? 1. If you had -1 to the 4th power, what is it? -1 to the 6th power. -1 to the 8th power. Right? Okay, not excited. -1, but to the 3rd power. Okay. So do you see how it's going to, I call it oscillating, because, I mean, that's the correct use of that word. So it's going to oscillate between positive and negative. So whenever you have a negative number raised to a power, you're going to have a situation where it's going to oscillate between positive and negative. So let's do one of these. So let's find, it says find the first 5 terms. So let's find them. So a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. Okay. Negative 1 to the first power we said was times the 5, negative 5. What's a sub 2 going to be? A sub 3. Do we see the pattern? Okay, so again, this chapter is patterns. So what happens here? It oscillates. So when we have an even n value, we're getting something out that's positive. And when we have an odd n value, we're getting something out that's negative. So it's going back and forth from one to the other. Positive, negative, positive, negative. All right. So even though we're only doing part of section 12.1, there's a lot of kind of beginning easy stuff. I feel like that happens in every section, every first section, right? It feels like there's a lot, but none of it's super tricky. That's where we're at again today. So we're going to do the next 2 pages still. Okay? All right. We're going to skip over this part, though, so you can cross out 3 and 4. We're not going to do that. But we are going to come down to this part where we're going to try to write the sequence. So, a minute ago, I gave you what a sub n was, right? And you just plugged in numbers for me. That wasn't too shabby, yeah? What if I gave you instead, the sequence, and then I asked you to find the formula for me? Like, what formula would result in this sequence? So that's what we're going to get into now. You can tell if something is linear because the first differences are the same. Let me show you what I mean by that. Let me make a little XY chart here. So we've seen tables before. I know we have. Let's say this is my table. It's linear if your first differences are the same. So what do I mean by that? First of all, your x values need to be evenly spaced, meaning they're the same step apart. Do you see how they're one step apart each time? Okay. When you go to your y values, do you remember subtracting from right to left to see if they were the same number? And that told you something about it? Yeah. Okay, so if we subtract from right to left, so let's start doing that. 23 minus 19 is 4. 19 minus 15. 15 minus 11, right? We see what's happening. So if it is changing by the same value, that would be my rate of change, and that would be meaning to me that it's linear. How do we find out if it's quadratic? It's quadratic when the second differences are the same. And this is going to help us figure out what type of equation we need, right? Because now we're working backwards and we're trying to find the equation. So should it be linear? Should it be quadratic? This is going to help us figure that question out. So the second differences are the same in this situation. So let me give you an example where that would happen. Okay. All right, so here's my new table. Do we agree that my x values are the same? They're one step apart every single time. Okay, that has to be true. Let's go look at our y values now. 26 take away 17 is what? 9. 17 take away 10. 7. 10 take away 5. And then 3, and then 1. Are my first differences, are my first set of differences all the same number? Nope, they're still different. So we're going to subtract again. 9 take away 7, 2. 7 take away 5, 2, 2, 2. So do you see how the second set of differences are the same? That's how I know it's quadratic. How could you tell if it's cubic? Third set of differences, and quartic, and quintic, and so on. Okay, so you can kind of see where that's headed. The other thing that could happen is that we could encounter exponential equations. We've dealt with those already this year. How do you know if it's exponential? Because you have a constant, ratio, or multiple. You can kind of say it either way. A tomato, tomato. So how do you know if something is exponential? Remember, exponential equations are where your x, or your variable, is up in the exponent spot. So your variable is up in the exponent. So you're going to have a constant ratio or a constant multiple of something, which means that you are constantly multiplying to find your next term. So sometimes you're going to multiply by a whole number, like 2, right? So it doubles, doubles, doubles. This could also be something that decays. So you could multiply by a half, and then a half again, and then a half again. So that's another situation. So let me show you a table that would represent that. So here's xy, 1, 2, 3, 4, 5, 6. So make me a table, add the same values I'm putting in it. So if I go through and I play this subtraction game that I was playing a minute ago, I'm never going to get the same number. It's never going to repeat as the same value. When that happens, then we go through and we try dividing instead. So I'm going to go right to left. So you go against the grain, which feels kind of weird, but I'm going to go right to left and I'm going to divide. 192 divided by 96. So the subtracting isn't, let's try that again. 192 divided by 96. So we get 2. What is 96 divided by 48? 2, right? So if you divide and you get the same number repeatedly, then we know it's exponential. So, and this is what we call our R value. So if you're asked for the constant ratio or the constant multiplier, this number that you repeatedly get is called your R value. It's your constant ratio or your constant multiplier. All right, let's make up some equations. Are you ready? Okay. And then we're going to talk about recursive formulas last. That's our last topic. All right, our first, okay, I kind of like to set them up like this. I'm going to show you the way I do it. I'm a very only child in that way. Like, I like to show you my way. All right, I like to rewrite the terms so that I can see the term number and also its value. Like, I like to be able to look at them right smack next to each other. All right, what do you notice is happening? Let me repeat, hold on, before you answer. What do you notice is happening in relation to the term number? And then what it equals? It's a squared. So, if I wrote my formula was n squared, would that work for all of you? If I plugged in my n value, would it give me the correct answer? Let's check. 1 squared. Plug in the 2. 2 squared. Plug in the 3.
Yes.
Plug in the 4. Do we see it now? Okay. So this would be our formula. So this would be my answer. So we're working backwards now. They're giving us the sequence, and they're saying, find me a formula, please. Okay? Next one. Again, I like seeing them right next to each other. If you don't need that in your life, don't do it. For me, it's like I'm a very visual learner, and I want to see the term number next to the term itself. If you don't want to do that or you don't feel like you need to, that's fine. Again, that's just who I am as a human. All right. So what do you notice in terms of like what's happening here? So it started with a third, and then what? So not multiply by 3, but multiply by another what? 1/3. So we're constantly multiplying by negative 1/3. All right, so let's start thinking about what type of formula this is. So we know we need a 1/3, yeah? Okay. Let's think about this in terms of the term number. So 1/3 to the first would give us 1/3. Will 1/3 to the second give us 1/9? What about 1/3 to the third? I'm not thinking about signs right now, by the way. What about 1/3 to the fourth? Would that give us 81? Okay. So I'm going to start by writing this. Is that good for starters? Okay. Now, I need the sign to oscillate. What did we talk about helps make my sign oscillate? A what? A -1. So let's expand our parentheses just a little bit and throw in a negative sign. Now let's double check and make sure this works. -1/3 to the 1. Good? -1/3 to the 2. Yep. So you want to go back through and check. But the nice thing about that is that you can check your work and you know if you're getting them right or wrong. So I love that about math, when you can check and make sure, like, oh, I feel good about this. All right, I'm going to skip over part C, but I'm going to jump to part D, because part D is kind of interesting. Oh, well, that one wouldn't have honestly been that bad, trust me. We could have done it. Okay, this one. A sub 1, -1. A sub 2, 2. I'm just rewriting it. Okay. So here I am with my terms rewritten. All good? Perfect. Do you see how when I look at these, I don't really see like a relationship between the term number and then what my value is? Okay, let's think about it from like a linear, quadratic, cubic sort of standpoint. Is there a constant change? Yeah. What is it constantly increasing by every single time? 3. All right. A sub n equals, so we're increasing by 3 every single time. Lovely. So I'm going to put the n here because this one will get 1, 3, right? And then this one will get 2, and then so on and so forth. Okay. Let's think about the first term for a minute, though. A sub 1, if I plug in 1, it's going to give me 3. What do I need it to be? Okay, so what would I need to add to the 3 to get it to be a -1? -4. So let's try this and see if it works. -1 times 3. Oh, no, we need a positive. No, we don't. Just kidding. Sorry. Plug in your 1. 3 times 1. 3 plus -4. -1. Plug in our 2. 3 times 2 plus -4. Do you see how it's going to work for all of them? So usually what I do is I plug in my rate of change first. And then I think, what do I need to add to get to that first term? Does that make sense? So that's kind of how my brain processes through. Okay, other type. Oh my.
What the heck?
That was impressive. Okay. Listening. The other type of formula that we have out there are recursively defined sequences. And recursively defined sequences are a little bit different. So, this happens when you are given the first term. So you're going to be given the first term. and directions, I call them directions, so I'm going to put it in quotes, and directions for how to get to the other terms. And I'll show you what that looks like in just a minute. Also, something that I need you to know, you're going to encounter this. A sub n minus 1, that means the previous term. So this means one term ago the value was whatever. So a sub n minus 1 means the previous term. Okay, so that's something, both those pieces of information. Flip when you're ready, and we're going to do a recursive sequence. I'm going to show you how to do it by hand and also on the calculator. Okay, ready? Flipperoo. All right, bless you. Do you see how it gave me term, oh, you can't see that. Do you see how it gave you term 1, and it says term 1 is 4? Okay, it wants me to find the first 5 terms. So I already know term 1 because they told me what it is. Do I know any of the others, though, right off the top of the problem? No. All right. Shh. Listen. This says, take your previous term, add 5, and double it. That's the directions of how we get to the next thing. So my previous term was 4. 4 plus 5 is what? 9. Double it, and you get 18. So this was 2 times 4 plus 5, and we get 18. So there's my previous term. That's where it went. So the next one, 2, what's my previous term now? 18. Yep, a sub n minus 1 means take your previous term and plug it in. So I'm taking my previous term, and there it is. So that's going to give me 23 times 2, which is 46. So a sub 4, what am I going to plug in for the previous term? 46. So that's going to give me 51,102. 2 times, what's my previous term? 102 plus 5, so that gives me 107, so 214. Does that make sense how we did that? Okay, now let's pretend somebody comes along and they said find the 20th term. How is that going to make you feel? Let's talk about our feelings. How's that going to make you feel? Tired. That's a fair answer. Sad. That's another good answer. What if I ask you to find the 100th term? Grumpy. Tired. Again, probably, right? So this is where we can do this on our calculator. Write down your steps, and I'm going to show you how to do this. So the steps are that you're going to press your mode button in a minute, not yet. We'll do it all together. You're going to press your mode button. You're going to go to y equals, and you're going to type in the information, and your calculator can do these for you. So grab a calculator. I have 2 bonus ones if you need one. Anybody need one? Yes, no? It's right there if you change your mind. Oh. There we go. All right. We're going to do the problem we just did. Okay? Here we go. Go to mode. Go to sequence. SEQ. Do you see it down here? Look where my blinky cursor is. Do you see SEQ? It's the only one we haven't used. Yay! We made it. We did all of the things. Okay. Then I'm going to quit back to my home screen and go to y equals. Ooh, look at all sorts of weirdness. Okay. We're going to start with term 1. So give me a 1 if it's not already there. It might be, it might not be. Put a 1 in if it's not. Then, what?
Yeah.
Ooh, oh. Oh my. Well, we're only going to have one U, so I think this is going to be okay. This must be newer software than my calculator has, is what it is. Okay, so let's see what we've got here and see if we can get to the same spot. That's an update that Pinky doesn't have. Yeah, can I show? Thank you. Okay, so here's the calculator with the update. Do you see how it's giving me multiple things? That means, okay, so sometimes when we get recursive formulas, they can go up to n minus 2. So like not the previous term, but the previous term. And in that case, you would have to give the first 2. That makes sense. I'll show you one in a minute. We'll talk about the Fibonacci sequence in a second, which is pretty awesome. And that's one where you would need the first 2. I think we'll be fine, I think we'll be fine. Okay. Mode. Sequence. All right. So then we want to type in our equation. So our equation was right here. This is what I'm going to type in. But I have to do it in calculator talk. Do you see how there's a 2? That's easy. Type a 2. Then, there's a parenthesis. Put a parenthesis. Then we need, do you see how we're in terms of U here instead of A? That's just what your calculator wants to use. So I'm going to use a U instead of an A. Hold on, I'm going to show you. Do you see your U button right here? Okay. If I hit second 7, I should get a U. So you could write that off to the side maybe. So second 7 gets the U's. Gets U, a U. Kind of a funny way to write it, but that's what I'm going to put. Okay. Then, in parentheses, we need n minus 1. So we can't do a subscript, so you're going to put a parenthesis. And we're going to use the variable key for the n. So the variable key gets you the n. All right, so there's my n. And then I need n minus 1. And I'm going to close that. And I'm going to add 5. And I'm going to close that. Okay? So we have 2. We had to make the U come up by pressing second 7 to get it to come up because that's the only way to get a U. And so now these match. And then this term is n minus 1, so we needed the n minus 1 in parentheses. And then we've got our plus 5 because that was here, that was part of our equation. Good? Okay. Then, what was your first value? 4. All right, now I'm going to go to my table. So hit second graph to go to your table. Do you see how it starts counting at 1, and then 2, and then 3? Okay, we have errors before that because, again, our domain was natural numbers. Now, let's say I want to go all the way up to 20. I'm less grumpy with this, but do you see how I'm still going to have to, like, arrow down a lot? Okay, so let's use the trick that we learned before. Hit second window. Where would I like my table to start? 20. Then hit second graph to go back to your table. And it's a super huge number because these tend to grow really quickly. So what is my 20th term? My 20th term is 7.34 times 10 to the 6th. So remember, e to the 6th on your calculator is really giving you scientific notation. It's really times 10 to the 6th. How could I jump to 100? Same thing, second window. I would like my table to please start now at 100. Second graph. And is this working for new software people too? Good news. Okay. You guys made me nervous because that has never happened to me before where people haven't had the new software in previous years. So this is a new find for me. Okay. So this one I get 8.9 times 10 to the 30th. Good? So do you see how your calculator can help you? Because otherwise you would not have been happy with me if you had had to find all those terms. Okay, last thing I want to talk to you about very briefly is the Fibonacci number sequence. It is so cool. Okay. It is called the oh wait, I'm going to spell it wrong. Hold on. Sometimes talking and spelling is not my strength. Sequence. Alright, so the Fibonacci sequence is a famous number sequence. One of the reasons why people like to use it is because it helps putting stuff in code. It also helps you coming up with passwords. Like, we're a world that's kind of password driven right now. I feel like a lot of times they tell you to come up with, these crazy passwords with lowercase, uppercase, numbers, all the things. So the Fibonacci sequence, like I said, can kind of help us in a couple ways here. All right, so I'm going to tell you what the first terms of the sequence are, and then we're going to go back to step 1. So here is the Fibonacci number sequence. I'm going to see if you can tell me what the next number is, actually. I'm going to stop there. I hear 6. Ooh, I hear 8. 8 is correct. What's the next one?
13.
What's the next one? Okay, people who are shouting them out, how do you know? What are you doing? You're doing the previous 2 terms added together. Okay, so that's the Fibonacci number sequence. Here's, okay, here's how you would write it, and also the reason for the software update in the calculator. Okay, so on the calculator, listen, we're almost done. On the calculator, it gave us a spot to put 2 terms, right? And that's for a situation like this, where we need the first 2 terms. Because to find the Fibonacci number sequence, this is the way we write it. We say, take the previous term and add it to the previous term. There's probably a better way to say that, but that's how I say it. So to get this, you take the 2 previous terms and add them together. And that would be your formula. Do you see it? Super cool number sequence. Okay. And ta-da! Here's your homework. Oh, you stop. You're fine. 3 to 6. 3, 4, 5, 6. 13, 14. 25, 27. Do you want more? Is that what you want more problems because you have a whole weekend?
Yes. Yeah, I agree.
No, because they're all different. No, they're all a little bit different. Can what? No, you need to practice it.
How about every time I